Welcome back, class. All right, let's take a look at ionic compounds. Particularly, we're going to look at type 1 and type 2 ionic compounds. So really the only difference between both of these is that type 1 is when we're working with what we call representative elements. So that would be just the non-transition metal elements. And then type 2 is where we're working with the transition metals. So you can see here that from the notes, just a little quick summary, these type of compounds will have a metal, which is the cation, and a non-metal, which is the anion. So let's just jump in and let's take a look. Classically, we go with something like sodium, and we're going to go with also chlorine. This is usually like one of the first ones you ever learn. So the first thing we always do is we take the element symbol, and then we're going to take an arrow, and what we're going to do is we're going to write an ionic equation to figure out what the compound formula is and the name. So if we go to our periodic table, we see over here that we've got sodium, and it has an oxidation of +1. And chlorine, we can see over there, group 17, all the way on the far right, and the non-metal, it has an oxidation of -1. So if we go back, we know that we need to write a +1 and a -1. The key here is that the sum of the oxidation numbers, we need this to equal 0. So if we take a look at this, we already have 1 plus a -1, that is already 0. So all we do is we take both of the element symbols, we bring them close together, and we now have our formula. So way we would call this, what we would do is we know this is sodium, this is chlorine. So right here we would call this sodium chloride. And the reason for that has everything to do with this part right here. We take the ending, we drop it, and we add IDE. So what we did was we dropped the ending of the chlorine name and we added IDE to it. We replaced it with that. So sodium chloride is our compound formula. So this is our ionic compound, and it's a type 1 because, again, sodium here in group 1, it's a non-transition metal, so that's how we know that it is a type 1. All right. Let's go with another example. So let's take rubidium. Group 1 again. You can see the RB, and let's go with a different anion. Let's go with sulfur this time. So we're going to take rubidium, which we said was in group 1. And we're going to take that with sulfur, and it's a -2. And the convention is to write the number first and then the charge on the anion, okay? So we can see here we have 1 plus a -2. That is not 0. We need this to equal 1. So if we realize that if we were to have 2 of these, then 2 times this 1 that is right here, even though we don't write it, it's understood that that's a 1 there. That would give us a +2. We realize that there's a coefficient of 1 right here, but 1s are understood in math, so we just don't write the coefficient of 1. So that's really 1 times 2 is a -2. And we can see that 2 plus a -2 is 0. All this is scratch work that I'm doing here with the problem. But you can see now if we had 2 rubidiums, all right, and 1 sulfur, this would come together. So the way you write this is the element symbol, and then as a subscript, you write how many you need when it's together in a compound. So we would have RB2, and then we need 1 of the sulfurs. So again, this would have to be rubidium. And then sulfur, you take the ending and you add IDE, right? So let me back this up, drop that off, add IDE, rubidium sulfide. Let's take a look at one more of these type 1 compounds. Let's go with something different. Let's go with magnesium. And let's go with nitrogen. Come back to our periodic table, we can see magnesium is in group 2, so it has a positive 2 oxidation. And then nitrogen, all the way over there on the right, we can see, if we go to the top, we see that it carries a negative 3 oxidation state. All right, so we go back, we know that we have a positive 2 and a negative 3. Remember, the number goes first, it's the convention, and then the charge. So we ask ourselves, what's common between 2 and 3? And the first number that comes to mind is 6. So we know we're going to need these to add up to 6, so that when we add them together, they equal 0. So that's easy to see that if we had 3 times 2, that would give us a positive 6. And if we had 2 times this negative 3, that would give us our negative 6. And 6 plus a negative 6 is 0. And so we know that we need 3 magnesiums and we need 2 nitrogens. So in the spirit of the naming system, we know that this would be magnesium. And again, we drop the ending and we add IDE. So I'm going to drop the ending and I'm going to add IDE. So magnesium nitride. Mathematically, we see what's happening here. Now I want to take a look at something more of a visual that is typically called modeling ionic bonding. So let's go back to our first example. In our first example, we had sodium and chlorine. So sodium has 1 valence electron that it wants to add elsewhere. And we remember this because there's sodium in group 1. And we can see that it has a positive 1. It wants to add 1 electron. If it takes the electron that's here and adds it somewhere else, then now this orbital here and this orbital here would be full, correct? So remember that. If you forget that, go look back at some of the other videos that I made prior to this, dealing with atomic structure, and that'll become very apparent. All right. And then chlorine, if we come back over here, you can see that it has a negative 1. Well, it already has 1, 2, 3, 4, 5, 6, 7 electrons, 7 valence electrons in this third orbital here, right? So we know it has 3 orbitals, and then the third orbital, it's full all the way to that point, so that means there's 7 of those there, correct? So let me back this up, clean this up, get that out of the way. We come back here, and so we know that the chlorine already has 1, 2, 3, 4, 5, 6, 7 valence electrons. And so what is going to happen is this electron is going to be transferred over from the sodium to the chlorine. Because remember, the sodium is adding an electron somewhere else, and the chlorine is taking away another electron from somewhere else, which makes it a chloride ion. So now we draw our arrow, and we see that sodium, if it gets rid of that 1 electron, it would be positive by 1. Okay. Now we see our chlorine. It already had 1, 2, 3, 4, 5, 6, 7. And so this 1 electron that's right here is now over here in this space right there. So I'm going to put that there for you to see. And now what we do is something in chemistry. What we tend to do is we draw brackets around things, and the bracket represents the concept of concentration, okay? So what we're saying is now all 8 of the valence electrons that we started off with 1 valence electron around sodium, 7 valence electrons around chlorine, and now all 8 of those valence electrons are around this 1 chlorine. So now this 1 chlorine atom is charged to become a chloride ion. And so now what we see is that this right here, we call this an ionic equation. Okay? An ionic equation. That's a little messy for you. And then when we look at this right here with the Lewis dots, this is where we're sort of modeling our ionic bonding. And what we see is a transfer of electrons. Okay? Let's take a look at our other example that we had. Okay, so we've got our rubidium. So there's 2 of those according to that subscript. According to that coefficient. According to this coefficient right here, we have 2 rubidiums. So, and each rubidium carries a charge of positive 1. So that means it must take 1 electron and add it somewhere else. And just in the spirit of what we did last time, I'll go ahead and make the electrons on the cations a different color so that it makes it easier for us to visualize the process. We have 1 sulfur up here. Remember, this coefficient is 1. 1s are understood. So we have this 1 sulfur. If we go back to our periodic table, well, we can do this 2 ways. We can look at the periodic table and figure out how many we need, or we can remember what we've learned, that if right now sulfur has an oxidation of -2, then what that means is it's going to take away 2 electrons so that its outer orbital can become full. So here's sulfur right here, which means it already has 1, 2, 3, 4, 5, 6 valence electrons. And now those 6 valence electrons, if it takes away 2, it would put 1 in this place and 1 in this place. All right, in this space. In other words, these are just concepts of space. All right, so let me clean this up out of here. Go back to what we had. And we know we have 1, 2, 3, 4, 5, 6. Okay. So we're going to show a transfer of electrons from the cation to the anion. Okay. Draw our yield sign. So we have 2 rubidiums that are now, because they've added that electron elsewhere, they have 1 less positive part, or 1 less negative part, so they're more positive. And now you should be able to see that this sulfur that was already like this, it now has the 2 valence electrons that were added from the rubidium, each of the rubidium, or we can think of it as the concept that it took away 2 electrons from the rubidium, which is why we write the negative symbol. Okay, and then we put the brackets around it to show that the valence electrons we're working with, all 8, 2 from each of the rubidium, and then the 6 that were on the sulfur atom are now concentrated around this sulfide ion. So now let's go take a look at our third example. Here we see we had 3 magnesiums, so let's go ahead and draw our 3 magnesiums. And we're going to add that to 2 nitrogens. Okay? We can see from this that magnesium has a positive 2, it's a positive 2 cation, positive charge, which means that there must be 2 on each of these, 2 valence electrons on each of these that can be donated, added elsewhere. Okay? Nitrogen is -3. So again, nitrogen is right here. And so that means it's already full up to this point. So there must already be 1, 2, 3, 4, 5 valence electrons. And if it takes away 3, you would put those 3 in there, in there, and in there. Those are those 3 spaces. Okay. I'm just going to back this up because I like to have a clean periodic table when I come back to it. Okay. All right. So that means that there's 1, 2, 3, 4, and then we'll just put it here, 5. 1, 2, 3, 4, and typically you will see it written like this. But I'm gonna leave it both ways here so that you can, because it's going to be more convenient for what we're going to do. But typically, this is the way that it is drawn. Typically, when we have 5, we start from the top when we start pairing them up. Okay, just keep that in mind. That'll make sense for some other lessons later as to why we do it. But they both basically mean the same thing. So this nitrogen is going to take away 1, 2, 3 electrons, and now there would be a total of 8 around that nitrogen. This nitrogen is going to take away 1, 2, 3 electrons. Draw our yield sign. We have 3 magnesium, and each of them added 2 electrons. We have nitrogen that had 1, 2, 3, 4, 5. Now we see that we have that each of them took away 1, 2, 3 electrons. And now all of those are concentrated around. They each took away 3 electrons, and we have a total of 2 of these. So what I just did here represents, again, the kind of modeling the ionic bonding, the transfer of electrons from the cation to the anion. All right, please go back, take a look at these, work on the problem sets that I have uploaded for you. As always, there's answer keys there. It's great learning with you, and I look forward to seeing you in another video here soon. Take care. Bye.